So picking up where we left off yesterday, we did the first derivative test, we did the test for concavity, and then we also found the points of inflection as well. So the next stuff that we had in this section was they say a particle is moving along the x-axis with position function x of t, find the velocity and acceleration, and then describe the motion of the particle for t greater than or equal to 0. So 28, we have x of t is equal to 3t squared minus 2t cubed. So I first need to find my the velocity and acceleration equations by taking the derivative. So the velocity equation would be 6t minus 6t squared. And then I'm going to eventually need this, so I'm going to do them like side by side instead. So like when I do the second derivative, because I'm going to end up solving something with that in a little bit with the second or the third part of the question. So then the second derivative, which gives me acceleration, would be 6 minus 12t. So part of it that they're wanting us to do is to find the position of the equation or the motion of the particle, I guess I should say. And so we're going to be looking at essentially, is it moving to the right or to the left, and then is it accelerating or decelerating? And so to do that, we're going to be using our first derivative and our second derivative at the critical points for those things. So I'm going to take and set this equation equal to 0 and solve. So I'm going to factor out a 6t, and I'm left with 1 minus t equal to 0. So I end up with that t is equal to 0, or that t is equal to 1. And then I'm going to go ahead and find the zeros of the second derivative as well, just because. So if we set that equal to 0, I get, let's see, negative 12t equals negative 6. So t equals 1/2. So I'm going to do a sign chart basically for each of these. So I'm kind of just keeping them on their own sides here. So I've got this one. Now, I can't go any farther left than t being 0 because they told me it's for, or I'm describing the motion of the particle for t greater than or equal to 0. So obviously we can't have negative time. So I don't need to go anything past that. This is getting plugged into the first derivative. So this is the sine of v of t, or we could say the first derivative, however you want to think about it. So I put 0 and 1 on there. So I'm looking at what's happening in these intervals. So between 0 and 1, I'd put in like 1/2. And so if I put that in here, I would get 3, and then minus, let's see, 6/4, 3/2. So 1.5. So that means that would be positive. And then if I put in, say, 2 for this other interval, I would end up with 12 minus 24. So that's going to be negative. So when it's positive, the function or whatever, it's increasing and it's moving to the right. When it's negative, it's decreasing and going left. So that's telling us which direction it's moving. And then the second derivative is going to tell us, obviously we'll look at concavity, but within concavity that tells us if we're accelerating or decelerating. So over here, basically same thing. I've got 0. I can't go any farther to the left than 0, but I have a t of 1/2, so I'm going to have to choose a number in between those values there. And this is the sign of acceleration, so a of t, or my second derivative. So if I choose 1/4 into my second derivative, 12 times 1/4, that would be 3. So 6 minus 3, that's positive. And then over here, I'll use 1. 6 minus 12, that's negative. So this first interval is concave up. Second interval is concave down. So if it's concave up, that means it's accelerating. And then where it's concave down, it is decelerating. So that's our things there. So increasing and decreasing, we hadn't really talked about that as far as like having any problems that like asked us that information. And then like on these, they're technically just asking me like about the motion of the particle. It's not really asking me if it's concave up or concave down, but that's just kind of a review of what we were doing yesterday with like the second derivative and stuff like that. But concavity will tell you if it was a particle, what would be happening to it, essentially. Any questions on those ones? So one other thing, technically, obviously we did the second derivative test back in 5.1. I'm just going to there's one problem in here that I'll do just as a refresher of the second derivative test, since that was before Christmas, because this is technically where they teach the second derivative test. We've just done so much with it. I'm just going to do a refresher. So number 36. We've got y equals 3x to the 5th minus 25x cubed plus 60x plus 20. All right, so I'm going to go ahead and find my first and second derivative. So the first derivative is going to be 15x to the 4th minus 75x squared plus 60. And then I'm eventually going to be finding zeros, so I'm just going to do my second derivative over here like I did in the last problem. So second derivative would be 60x cubed minus 150x. So the only thing I'm really using the second derivative for is obviously plugging in the values that I get for my critical values from the first derivative. So one thing that I notice about the first derivative is I can divide everything by 15, so that's gonna like kind of simplify things down for us. So I'm gonna set this equal to 0 and factor out of 15. So I have x to the 4th minus 5x squared plus 4 equals 0. And then basically that 15 is just going to go away because I can divide by that. So now essentially I need to factor this. Now you may be able to recognize it and see that this is essentially just like our normal like x squared plus or minus 5x plus 4 kind of a deal. And you can treat it kind of that way. But what I do a lot of times is I use U substitution, which will kind of be just like an intro. I think I may have done one problem like this last year in pre-cal just to like show you what U substitution was. But it's essentially, I'm just going to say let U equal x squared. And then I'm going to rewrite this equation in terms of u's instead of x's. So I'll have u squared minus 5u plus 4 is equal to 0. And then I can factor this down, or I can factor this. Once I get kind of like far enough into the problem, I'm gonna like essentially once it's factored, I have to take and plug x squared back in for u. But it just kind of makes life a little bit easier to like visualize it and stuff, especially with like factoring. So this would factor into u minus 4 and u minus 1. And if you can see it without doing the u substitution, don't feel like you have to do it. But anyways. So then at this point, now I would, as I'm getting ready to set each piece equal to 0, I'm going to go ahead and replace u with x squared again. So I've got x squared minus 4 equals 0 and x squared minus 1 equals 0. And so then x squared equals 4. So then x equals plus or minus 2. So I'm going to have those two things to check. And then over here, x squared equals 1. So x equals plus or minus 1. So I have 4 different values that I'm going to be checking in my second derivative now. AirPods are just falling apart. All right, so over here in my second derivative, I'm going to plug in these points and basically remember if it's less than 0, it's a max. If it's greater than 0, it's a min. And so we've got f double prime of negative 2. So if I plug in negative 2 to this equation, it's going to give me a positive 300 and it's a negative 8, negative 480 plus 300, so negative 180, which is less than 0, so that means that I have a max at x equals negative 2. I could find the original point if I wanted to, if I was so inclined by plugging it into the original, but I'm not going to do that right now. I have double prime of 2. Essentially, that just gives me 480 minus 300, so that's going to be a positive 180, which is greater than 0, so that means that that's a min at x equals 2. Then I'm going to do negative 1 and positive 1, so f double prime of negative 1. That's a negative 60 and a positive 150, so that's going to give me 90, which is greater than 0, so that means that that is a min at x equals negative 1. And then f double prime of 1. If I plug in positive 1, I'm going to get 60 minus 150, so that's negative 90, which is less than 0, so that means that that is a max at x equals 1. So just another method, obviously, that we have outside of the, all the other ones that you now know how to do. So, and then obviously with the second derivative, we can use that to help us find our concavity and all that as well with the sign chart. So, any questions on that? Vaguely remember it from before Christmas?
Yeah.
Okay, so problems. I didn't give you any yesterday, right?
Mm-hmm.
Okay. Let's see here.
So if we did a sign chart for this one, we would put all those points on the sign chart?
Yeah.
Okay.
Well, these were first derivative points, so technically we would do, well, are you talking about concavity or what?
Yeah.
So for concavity, that's the second derivative being equal to 0. So where is it?
Oh, okay.
Yeah, so we take the second derivative, set it equal to 0, and then do that. So
Okay.
if we were to do that with this problem, basically, I would take out, 30x, I guess, and then be left with 2x squared minus 5. and then I would do it that way. But obviously that's going to end up causing you to have some non-real numbers that we would have to ignore, because obviously you can't have that. So we'd end up really only having one number that we would actually be testing for concavity, I think, technically. But concavity is going to change between your mins and maxes as well, so you can kind of see that with that method, if you're so inclined that way. And then the points of inflection are occurring where the concavity is changing as well, so you can see that with your value. If the concavity changes, like negative to positive, positive to negative, then you have a point of inflection, which you plug into the original to see what those are. So let's see some problems. 1, 3, 7, 13. 17 is going to be a little bit more challenging, to potentially, depending on how you go about doing it. And then 27 and 35. Try to hit a little bit. And obviously, if you need to do more of a specific type, that's like 1 or 2 of each type, pretty much there.